Hello dear students. Today we are going to discuss about solutions of state equations. So here we will discuss the solutions of state equation in two cases. First of all, we will assume that the system has no inputs. In that case, we can say it as a homogeneous equation. So we will find the solution of a homogeneous equation, and in the second case we will be giving an input. So that equation corresponding to the system will be a non-homogeneous equation, and in that case we will find out the solutions for non-homogeneous equation. So we are discussing it in two cases. First is solutions of homogeneous equation, second is solutions of non-homogeneous equation. Let us see. We are considering the system has no input or excitation. So we will find the solutions of the state equations without input or excitation. Consider a first order system and which is represented by the differential equations with the initial conditions x of 0 equal to x0. So the first order system can be represented by the differential equation dx by dt equal to ax. And here the initial condition is x of 0, that will be equal to x0. So we can, in order to find the solution, we can make a simple rearrangement, that is dx will be equal to ax into dt, and here x can be taken to this side, so we will get dx by x equal to a into dt. So if we are integrating this, we will get, whenever we are integrating dx by x which is equal to integral a dt, we will get log x equal to at plus c, where c is a constant. For finding the constant value, we can make use of initial conditions. See, here x value can be obtained by taking the anti-logarithm. So x will be equal to e raised to at plus c. So this can be written as e raised to at into e raised to c. When t equal to 0, we can find the initial condition, that is t equal to 0. That means x will be equal to x of 0, and this term will become e raised to c. Okay. So x of 0 equal to x0, that is obtained in the initial case. So x0 will be equal to e raised to c. Okay. So we can substitute this in the equation for solutions. That is equal to, we have the equation x equal to e raised to at into e raised to c. Now we obtained e raised to c equal to x0. So we can substitute this value here. So we will get x will be equal to e raised to at into x0. So this is the solution of the first order differential equation with the 0 initial condition, with 0 input. Okay. So x equal to e raised to at into x0. So in that case, we know that e raised to x has a form 1 plus x plus 1 by 2 factorial x square plus etc. up to 1 by n factorial and x raised to n plus etc. So this is the form of e raised to x. See, this condition 4.47 can be substituted in 4.46. See, this is instead of e raised to at, we can substitute this equation. So instead of x, here at comes. So we can write x will be equal to e raised to at equal to x0, that equal to 1 plus, instead of x at comes, here also at comes. So we will get an equation like this, and x0 is outside. So we know that in the case of the state equation, what is the state equations? It is represented by x dot of t equal to a into x of t plus b into u of t. Here input is equal to 0, so b into u of t term will be equal to 0. So x dot of t equal to a into x of t. This is the state equation corresponding to a first order system. And also it is given that x of 0 equal to x0, which is the initial condition. So here we can write x of t is equal to, in terms of this thing, we can write it as, if you are multiplying 1 with x0 and at with x0, we will get a into x0 into t, where a into x0 is a constant. So we can write, since x0 is a constant, we can write x of t as a0 plus a1t plus a2t square plus a3t cube plus etc. So here a0 is x0, because it is a constant value, we are notating it as a0, and a into x0 is another constant, we are notating it as a1. 1 by 2 factorial into a square into x0 is another constant, we are representing it as a2. So this is the notation. Here a0, a1 etc. up to a are matrices. When we are notating it in the matrix form, these all represents the matrices. So now we have x of t in this form. So we can write it as this equation, and when we are differentiating this equation, what will be obtained? First differential of x of t is x dot of t, that will be equal to a1 in a1 plus c, you will get a1 plus 2a2 into t plus 3a3 into t square. That is the differential of this equation. Okay, this is a constant, so this will differential value will be equal to 0, and this will be equal to a1, this will be equal to 2a2 into t plus this will be equal to 3a3 into t square plus etc. So in general, here if we are multiplying, see what we want is we have a x dot of t equal to a into x of t. Now we have a x dot of t here, and what is x dot of t? X dot of t is obtained by multiplying s of t by a. So here is x of t. When we are multiplying this with a, we will get a into x of t will be equal to a into what is x of t? X of t is this, x of t is this one. Okay, this is the equation, so we can multiply this. Okay, so you know that x dot of t equal to a into x of t in the case of a homogeneous equation. So we can equate these two, and we can equate the quotients of t square, t cube, like that. So you will get a1 will be equal to a into a0, and you will get 2a2 will be equal to a0 into a1. Similarly, you will get different terms, and when you are rearranging the terms and make sufficient substitution like this, see a1 equal to a into a0, 2a2 equal to a into a1. Here you can substitute a2 equal to 1 by 2 into a into a1. When you are substituting a1 equal to a into a0, you will get a2 will be equal to 1 by 2 a square into a0. Similarly, you can make the same substitution in the other terms also. So you will get a general form ai equal to 1 by 1 factorial into ai into a raised to I into a0. So here you can write x of t will be equal to a0 plus a0 plus 1 by 2 factorial into a square a0 t square plus etc. See, that is obtained here. You have this term a1 a2, instead of a1 a2 a3 etc. you can substitute these values. A1 is equal to a into a0, a2 equal to 1 by 2 into a square into a0, like that. So you will get an equation of x of t like this. So here when you are taking a0 outside, see a0 aa0 etc. are matrices. When you are taking a0 outside, here an identity matrix I comes plus here a into t comes. When a0 is taken outside, here also other terms will be like this. Here I is a unit matrix, and when we are substituting t equal to 0 in this equation, therefore x of 0 will be equal to all other terms will become 0, and this will be equal to I into a0. That is x of 0 become equal to a0. So you can make substitutions like we have x of t in this form, right? Okay, you have obtained that x of t equal to this term, right? And this is what is, this is written here. Okay, x of t equal to this term, and here you can write this will be similar to e raised to x term. So you can write this is, instead of x you are getting at. So you can write instead of this term as e raised to at. So x of t will be equal to e raised to at into x0, where x0 is obtained by x of t at t equal to 0, and e raised to at is called state transition matrix. So what is the meaning of this equation is that the matrix e raised to at is called the state transition matrix, which is represented by phi of t. In some notations, e raised to at is notated by phi of t, and this is the solution of the homogeneous state equations, that is x of t equal to e raised to at into x0, and it is obtained at t equal to 0, and x0 is the initial condition. And this is what is its meaning is that the state transition matrix makes the value of x of t to this value whenever t equal to t0. That is x of t will be equal to e raised to at into x0. That is, from the solution of the state equation, it is observed that the initial state x0 at t equal to 0 is driven to state x of t at the time by the state transition matrix. So initial state is transferred to this state by using the state transition matrix. Here state transition matrix is e raised to at, that is represented by phi of t. So this is the solution of the state equation, that is solution of the homogeneous state equation. That means the solution of the state equation whenever input equal to 0 is x of t equal to e raised to at into x0. Here e raised to at is called state transition matrix. Okay. So next we will discuss about a non-homogeneous state equation. That means there will be some input there. So what will happen to that case? In that case, the system is represented by the state equation x dot of t equal to a into x of t plus b into u of t. In the previous case, since there is no input, so this term was 0. Here there will be input or excitation. That is why we are representing the system by x dot of t equal to a into x of t plus b into u of t. Here also initial condition is x of 0 equal to x0. So we can write here x dot of t, when you are taking this quantity here, you will get x dot of t minus a into x of t equal to b into u of t. If we are multiplying both sides by e raised to minus at, then you will get e raised to minus at into this term equal to e raised to minus at into b into u of t. So you can multiply the quantities inside the bracket, so you will get this equation. So here you can substitute instead of this term by a term d by dt of e raised to minus at into x of t. See, when you are taking the derivative of e raised to minus at into x of t, you will find that its derivative is e raised to minus at into x dot of t plus e raised to minus at into minus a into x of t. So this is this equation. So instead of this equation, you can substitute this d by dt of e raised to minus at into x of t. Right side is the same. So you can write d by dt of e raised to minus at into x of t equal to e raised to minus at into b into u of t. So now your equation changed like this. So here you can take this dt to right side and you can integrate this equation. So you will get at the left side it become e raised to minus at into x of t. And the right side, you know that when you are taking the integration, you will get a constant of integration, that is x0 plus the integral of rest of the terms, that is equal to integral of 0 to t e raised to minus at into b into u of tau into d tau. Here tau is the variable of integration. It is a dummy variable substituted for t. So this is your equation now. So if we are multiplying both sides by e raised to at in order to cancel this term, so you will get x of t. See, when you are multiplying this with e raised to at, this become 1. So x of t equal to e raised to at into x0 plus e raised to at into integral 0 to t e raised to minus a tau into b into u of tau into d tau. So you will get this equation. So this will be the solution of the non-homogeneous state equation. So you can rearrange it. See, here x of t is equal to e raised to at into x0 plus integral 0 to t into e raised to at into e raised to minus a tau into b into u of tau into d tau. So this is obtained by multiplying the entire equation by e raised to at. So this equation inside the bracket you can write e raised to a into t minus tau into b into u of tau into d tau. So this is the solution of the non-homogeneous state equation. That means whenever we are giving an input to a system, then the corresponding state equation has a solution like this. So in the previous case, the solution was this only term. That is in the case of homogeneous equation, solution is this one. But in the case of non-homogeneous case, the solution is this one. So you should remember this equation. And here e raised to at is the state transition matrix at t equal to t0. t equal to 0. So this equation is a solution of the state equation when the initial conditions are known at t equal to 0. Suppose if the initial conditions are known at t equal to t0, then the solution of the state equation become x of t equal to e raised to a into, we are knowing the solutions at t equal to t0, so the t will be replaced by t minus t0 into x of t0 plus e raised to t0 to t e raised to a into t minus tau into b of u of tau into d tau. Here the state transition matrix is e raised to at and that is denoted by the symbol phi of t, that is phi of t equal to e raised to at. Here there is another matrix, so this can be represented by e raised to a into t minus t0, that will be equal to phi of t minus t0. Similarly, e raised to a into t minus tau will be equal to phi of t minus tau. So you can substitute. So you will get x of t equal to phi of t into x0 plus integral 0 to t into phi of t minus tau into b into u of tau into d tau is the solution of the non-homogeneous state equation when the initial condition is known at t equal to 0. So similarly, we can write at t equal to t0 when the initial conditions are known. Then the corresponding solution of the non-homogeneous state equation is x of t equal to phi of t minus t0 into x of t0 plus integral t0 to t into phi of t minus tau into b into u of tau. Here this is representation for state transition matrix. So this is important thing. So you should know this solution of a homogeneous state equation and also the solution of the non-homogeneous state equation. And in all these cases, there will be a state transition matrix. So state transition matrix converts the initial condition to the solution x of t. Okay. So next let us see what are the properties of the state transition matrix. And it is asked for one university question. So first property is that phi of 0, that means t equal to 0. So e raised to at is phi of t. So instead of t we can substitute 0. So that will be equal to 1. That means it is a unity matrix. That is first property. Second property is that phi of t equal to e raised to at. But when we are taking inverse or when we are inversing the time, so you will get e raised to minus at all inverse, which is equal to phi of minus t all inverse. That means phi inverse of t will be equal to phi of minus t. That is the second property. And third property is that whenever time is changed to t1 plus t2, that means phi of t1 plus t2 will be equal to e raised to a into t1 plus t2. That will be equal to e raised to a t1 into e raised to a t2. That will be equal to phi of t1 into phi of t2. So when you are changing the time to t1 plus t2, then the corresponding state transition matrix will be individual state transmission matrix multiplied, that is phi of t1 into phi of t2. So these are the properties of state transition matrix. This is an important thing, and also you should remember the state equations, solutions of the state equations that is in terms of the state transition matrix. Okay, in the next video we will discuss about the state transition matrix calculation. So if you have any doubt you can ask me. Thank you.